Hello folks, welcome to CodeCrux. In this video, we will discuss the equivalence of DFA. That is, if we are given two different DFAs, then we will check if they are same or not. So let us understand how we can check the equivalence of two different DFAs. Consider machine M1 looks like this. If it generate the language produced by this M1, then initial state is the final state. So definitely epsilon would be the part of the language generated by this machine M1. If we read first one, we are going to non-final state, that is B. When we read second A, we are going back to the final state. So 2A are accepted. When we read third A, we are going back to non-final state B, and when we read fourth A, we are coming back to A. That is acceptable. So 0 is accepted, 2 is accepted, 4 is accepted. So if we follow this pattern, then we can easily visualize that the accepted set of strings would be even number of A's, that is 0A, that is epsilon, 2A, 4A, 6A, and so on. So in general, we can write L1 is equal to A power n, where n is even. Right? It could be 0, 2, 4, 6, 8, or anything. Let us consider another machine M2, which looks like this. Let us produce the language generated by this machine. A is not a final state, so epsilon cannot be the part of language. When we read first A, we are going to B, and B is a final state, so 1A is acceptable. When we read second A, we are coming back to A, which is not final state, so 2A are not accepted. When we read third A, we are going back to B, so 3A are accepted. Fourth A will lead us into state A, which is not accepted. Fifth A will be accepted. So if we look at this pattern carefully, then this machine is having language A, AAA, 5A, 7A, and so on. Or we can represent this L2 as A power n, where n is odd. So definitely these two machines are not same because their languages are different. So these two machines are not identical, or they are not equivalent. So M1 is not equal to M2. Let us consider another scenario where we have some machine M2 which looks like this, and we will try to derive the language generated by this machine. So initial state is the final state, so definitely epsilon would be the part of the language generated by M2. If we read first A, we are going to B, which is not acceptable. When we read second A, we are going to capital C, so that is acceptable. It means we have read out 2A, we are in final state. When we read third C, we are coming back to B, not accepted. Fourth A from B will lead us to C, that is acceptable. Then fifth not acceptable, sixth A acceptable, seventh not acceptable, eighth would be acceptable. So we can say that L2 would be epsilon, then 2A, 4A, 6A, and so on. And we can represent these languages L2 is equal to A power n, where n is even. So machines can have different representations like M1 and M2, but they could produce same language. If they produce same language, we will say that machine M1 and M2 are same. So if we are given simple machines, it's easy to find out whether they are same or not. But when we are given big machines, very complicated machines, then this exhaustive approach will not work. That is difficult to identify whether they are same or not. Right now only one symbol is involved. There could be multiple states and multiple symbols. So that makes our task very difficult. So we will learn a proper way of comparing two different machines. So two finite automata M1 and M2 are said to be equivalent if language generated by M1 is the same as language generated by machine M2. And M1 and M2 are not equivalent over given alphabet set sigma if there exists some string W such that W belongs to language generated by machine M1, but it is not part of language generated by M2. Or it could be vice versa. The W is not part of language generated by M1, but it is part of language generated by M2. So if we can find at least one string which satisfy one of these two conditions, it means machine M1 and M2 are not equivalent, or they are not same. So assume that we have machine M1 we have already discussed the properties or how to represent DFA. If you have not watched that video, then I insist that you first go and learn the representation of the DFA. The link of that video is given in the description box. So we represent DFA using 5-tuple notation. So M1 is defined by capital S, sigma, delta 1, S0 and F1, where capital S is set of the states in machine M1, sigma is set of symbols used to construct the language, delta 1 is the transition rule to construct the language, S0 is the initial state of machine M1, and F1 is the set of states of final states of machine M1. Similarly, M2 is defined by Q, sigma, delta 2, Q0 and F2, where Q represents set of states of machine M2, delta 2 is transition rule for M2, Q0 is the initial state of machine M2, and F2 is set of final states of machine M2. Now to check the equivalency, we have to construct a combined machine M3, and this M3 is defined like this. It is given by the Cartesian product of S cross Q. So S is set of states in M1, Q is set of states in M2. Then sigma would be same. Then we have to construct a new delta transition function. Let us label it as a delta 3. And initial state of new machine would be S0, Q0. That means combination of initial state of M1 and initial state of M2. So now every state in combined machine M3 will have two entries, or it will have two symbols, one from M1, one from M2. So initial state of combined machine would be the S0, Q0, that is the initial state of M1 and initial state of M2. And we will have F3, that is the set of final states for this combined machine M3. State of M3 will be in always form of Si, Qj, where Si will be always from capital S, that is a set of states from M1, and Qj will always belongs to capital Q, that is set of states in machine M2. The transition function delta 3 will be always S cross Q to S cross Q, and it is defined like this. S3 delta 3 would be some state from this combined machine M3, that is Si, Qj, and AK is some alphabet from sigma. Okay? So that could be small a, small b, small c, etc. And this delta 3 we can rewrite in form of delta 1 and delta 2, because delta 1 and delta 2 are known, because machine M1 and M2 would be given. So if we can break this delta 3 as like this, we have to apply delta 1 on state Si for input alphabet AK, and delta 2 we have to apply on state Qj for the same alphabet AK, and that will give us the new state in machine M3. And this process we have to repeat all the alphabet symbols in sigma, A, B, C, D, whatever number of symbols are given. So let us understand the algorithm for constructing this combined machine. So the first step is we have to add the combined initial state, that is S0, Q0 to machine M3. Then for every state Si, Qj in M3. Okay, so now we have to treat, or we have to process the states of M3 only. So S0, Q0 is already added. So we have to read that S0, Q0, and for that state we have to do the following process. If new states are generated, then for those new states in M3 we have to repeat this loop. So for every state Si, Qj in M3, what we'll do, if Si, Qj has not been expanded. Expanded means we have not executed delta 3 rule on that. If it is not done, then we have to apply delta 3 for this particular combined state. In that case, for each alphabet AK belongs to sigma. Now we have to take the unexpanded combined state Si, Qj from M3, and we have to apply that delta 3 transition rule for every alphabet belongs to sigma. So we have to add the transition delta 1 Si, AK and delta 2 Qj, AK. So Si is a state from machine M1, Qj is a state from machine M2, and AK is the alphabet from the sigma. Fine. So delta 1 is the transition rule of M1, delta 2 is transition rule of M2. When we combine this, we will get the new state in M3. Now this newly generated state may be totally new or it may be already existing in M3. And if it is not expanded, then we have to do it. If it is already expanded, we have to skip that. And when all states are expanded, the algorithm will stop. So once machine M3 is derived, now we will check for the equivalency of these two machine M1 and M2. M1 and M2 are equivalent if, now we will do the check on every state of this machine M3. For every state Si, Qj in this combined machine M3, both Si and Qj are final states or both Si and Qj are non-final states. If these conditions are true for every pair Si, Qj in M3, then we will say that machine M1 and M2 are equivalent or they are identical. And M1 and M2 are not equivalent if for any pair, maybe one pair, two pair or at least one pair, if Si is final state and Qj is non-final state or vice versa, that is Si is non-final state and Qj is final state, then we will call that M1 and M2 are not identical. Thank you. That's it for today, folks. See you in next video. If you think this video was useful to you, then please like, comment and share. Don't forget to subscribe the channel Code Cracks. Press the bell icon for the notification of latest videos. Stay connected, stay tuned. Thanks for watching. Bye-bye.